Okay. From yesterday, we were talking about end behavior. Can someone help me out and give me the easier explanation for what this is referring to and what this is referring to? Okay. So as x goes to positive infinity, is as you head, can I say head right or head to the right? We could say if x goes to the right, but we can also say, x does move right left. So as we head to the right of a graph, and then this one, x goes to negative infinity, as we head left, right? Now, this notation is new, right? Little arrow meaning going towards and infinities and negative infinities. Real quick reminder, what does f of x represent? Y heights. How high up, how high down, right? So if we think about a negative cubic, oh, there's extra stuff. Who cares? We're not looking at the inside as to whether it curves or whether it's flat or whether it's stretched or any of that sort of stuff. We're just looking at the outer parts. A cubic function, if it's negative, is it going to go the normal way? It's going to be reverse. Now, can I graph that and say it looks just like that? No. But what can I do?
You can describe the end.
Think about the ends. Think about the ends. Think of a cubic function, a normal one. Remember parent function x cubed. If I flip it, there it is. And then think about, okay, there could be all sorts of different stuff going on in here, right? It could be like weird, like swoopy swoop. It could be straight. Well, straight. Flattened. I only care about the ends. So what is this saying? As we go to the right, visualize, where's it headed? Down. Which means f of x is going to negative infinity. The heights are going down. Okay, as I go to the, ready? Eyes up here. We got this. As we go to the left, where's it going? Up. And how do we describe that with our new notation? Y's go up. Positive infinity. Right? So looking at this one, he's an even function, like a parabola. Is it a positive parabola or a negative parabola?
Positive.
Right. Now, could it be like a weird swoopy swoop? Yes. But we're not looking in the inside or the middle. We're looking at the ends. That's all we're caring about. And the ends will mimic the parent function. So, as I go to the right, where is f of x going? Up. And how do I show that? F of x? Positive infinity. Because positive infinity would be up, negative infinity would be down. So what am I going to say as I go to the left? F of x approaches infinity as well. Silly way of saying it. To the right, up, to the left, up. But that's just a nice way of writing it. And we're learning new notation. Yeah, Jessica.
So, when doing these kinds of problems, should we just have all of the different shapes memorized for each?
I think it's probably easier to visualize the graph and then code to this than try to go straight to the notation. Yeah, I would agree. But some people aren't as visual maybe as others, so maybe that's just like an extra busy work that they don't need. But I think visualizing is probably the easiest way to go. So then the last one. Is it flipped or is it normal?
It's normal.
Normal. And it's odd, so I'm looking at this one, right? Not caring about what's going on in there, because I don't honestly know. But we're looking at the ends. How would we describe what's going on to the right? F of x, the y's go to infinity. And as I go to the left, now, let's see. Even though the middles might be different, if the graphs seem to agree. Look at the ends. Who cares about the middle? We're just looking at the ends. Did I get the ends right? Nice. Okay.
I like that one's like a nice building.
Nice little W centered around the middle. I guess they're all centered around the middle.
I wrote back with the one on the right.
Personal preference. Yeah, the one on the left is a bit extreme. All right, let's keep going. Poor little functions, judgment all over the place. Here we go. Finding zeros. Finding zeros. Quick review, zeros, what are they again?
Roots.
X. Intercept. Finding the zeros. And if you guys look at the little squiggle and statement right after, we're thinking about the maximum number of zeros a polynomial might have. The maximum number of zeros a polynomial might have. Depends on the type of polynomial. Some, well, when thinking about minimum, I should say. Some don't have to have any zeros at all. Maybe you can think of which ones. Some have to have at least one. But depending on the degree, they might have a whole lot more. There are actually a couple of characteristics that are also up here, but they all kind of relate to the zero question. They all kind of relate to the zero question. Now we're not going to go super intense into finding zeros in this section. We're still kind of towards the beginning of chapter 2. We are going to work much more on finding zeros, aka factoring polynomials.
Yeah.
Factoring higher powered polynomials later on in the chapter. It has its own section. Synthetic division, the remainder factor theorems. But that's not today. And that's not this section. Okay? So this is just the beginning. I know, he's ready. But I know it's working. Okay. First of all, a polynomial has at most n. Wait, who's n again? Quick review. N is the in the very first page, that nasty definition of a polynomial. Who was n? Section 2.1. The degree. And the degree stands for the highest power of x, right? So the highest power of a quadratic is 2. The highest power of a cubic is 3. The highest power of a quartic is 4, etc. Right? So a polynomial has at most n real zeros. It might have fewer. We'll talk about why in a second. It has at most n take away 1 turning points. And the turning points would be for a polynomial. Remember, there are smooth terms. There are smooth terms. The turning points would be maximums and minimums. Uh-oh, wait a minute. I just said it plural because a function might have more than one, right? Or like the W, more than one. Ish. Okay? But maximums and minimums will always occur when a function, a continuous function, changes from going up to going down or going down to going up. Just a quick little preview of what's to come. Finding zeros then. Now remember, I want you guys to actually put in parentheses. This is just the beginning, right? You guys know from last year, factoring cubics and quartics and all that stuff. There might have been some rough patches for factoring. So either these ones will be easy or, well, we'll do the best we can with them. Bless you, bless you. But no synthetic this section, not specifically. I'm not teaching it, I'm not going over it. No polynomial division this section. No testing of different zeros necessarily this section, okay? Let's keep going. Don't worry, we'll apply this in a second. We have a function. Why did I say finding the zeros is just the beginning? What do you notice about this function?
That's something.
It's not hard to factor because all you do is take out the greatest common factor of -2x squared. Now, is this a quartic? Yes. What? A polynomial with a degree of 4. Like 4 quarters in a dollar. Quartic? Yes. But his factoring, careful, check it. Negative times a negative is a negative. Negative times a negative is a positive. Sorry, negative times a positive is a negative. Negative times a negative is a positive. His factoring isn't that hard because what can I do now that I have it down to x squared minus 1? Difference of squares. Finding all the real zeros. Oh, zeros, that's right. Set everything equal to, set the y equal to 0. And how do I solve? Some of you might need to remind yourself by putting a parenthesis here. To find zeros, we take each and every factor and set each and every factor equal to 0. Got it. So if I set x squared equal to 0, can you make that jump? If x squared equals 0, then x equals 0. If x plus 1 equals 0, subtract the 1, I get a negative 1. And if x minus 1 equals 0, add the 1. Are we okay? We would have 3 little baby equations, set them all equal to 0 and solve. Jesse?
So we don't do anything with negative 2.
No. Just because negative 2 equals 0, oh, it's not possible. So negative 2 can't make the 0. Only these pieces can. Does that kind of make sense? Hold on, real quick. Just from what we saw on the page before, what's the maximum possible number of zeros that a quartic could have?
3.
N. And what's N in for a quartic? 4. But he only has 3. What does that mean? Well, we'll see the graph in a second and we'll know what it means. Hang in there. Maximum number means either 0 or 1 or 2 or 3 or 4. 0. Talk about that too. Okay, we have 3 different intercepts. Maximum turning points. Look in your notes.
That's just
4? No. And minus 1. 3.
3
Maximum turning points are going to be 3. Okay? Because what is my n for a quartic? It's a 4th degree polynomial. And for maximum number of zeros in the base of 4, that's going to match up. For turning points, take away 1. Every time. N minus 1 maximum turning points. Okay? There's a real quick little repeated zero note. When factors are raised to a power, we call them multiplicity. For this problem, based on this note, we could actually come back up here and say the following. We have a repeated 0 at x equals 0. And we could say that 0 has a multiplicity of 2. Why? Why is it repeated?
Because you have 2x is equal to 0.
I could technically take this and I could make this x times x, and I could have 2 separate factors. The quartic can have up to 4 factors because x times x times x times x is x to the 4. It can have up to 4 factors, but what's true about this one? It's repeated. So then both of them have the same answer, multiplicity of 2. There's a double 0 at 0.
But
In essence,
But the graph still looks like it has 3, right? It's not like
the graph looks like it has 3, but there are 2 branches of the graph that only hit at 1 0, instead of each branch having its own 0. We'll get back to that in a second.
What's the multiplicity?
Multiplicity just means, like if this was an x cubed, it'd be a multiplicity of 3. So it's like how many factors have that 0 of 0. So we say 2 because there are just 2 x's. Let's keep going. Long story short, hold on, pause. We want to get to where we can get a really good sketch of this. You're like, oh. But these are all clues to help us get there. So we have the zeros. We know the maximum number of turning points. We know there's a repeated 0 at 0. Those are all clues. We're not going to put them together yet because that's not quite enough information to graph it yet. But we're almost there. We're almost there. Let's get another clue. We have zeros. We've talked about turning points. Now sign charts. I'm going to give you guys a second to write this down. right now this is general. When I start writing in red, I'm going to make it specific to the problem at hand. But right now this is a general sign chart. Doesn't that look like a number line though? Looks like a number line to me too. We're going to call this sign chart because it deals with the signs of the function. Where the y's are positive or where the y's are negative. There's a snazzy theorem, it's actually at the end of this section before the homework. There's a snazzy theorem called the intermediate value theorem. Intermediate, kind of like an in-between. You're not quite advanced. Like an intermediate, how is it used? You're not a beginner, but you're not advanced, you're intermediate, you're in between. Intermediate value theorem, in between values. That helps us with this. That basically says if a function is continuous, can be drawn without picking up your pencil, that's the easy way of saying it. If a function is continuous, which polynomials are, the only way to go from positive numbers to negative numbers, positive heights to negative heights, or vice versa, is by crossing through the zeros. Only way to move from positive numbers to negative numbers of a continuous function is through a zero. So what we do is we take the example like the page before, which was it was negative 2x to the fourth, right? Plus 2x squared? And we got the zeros to be, at the end of the day, x equals 0, negative 1, positive 1. We take those zeros and we mark them on the number line. So we take x equals 0, negative 1, positive 1. And we say, hey, this function can only pass from above to below or below to above at these 3 points. So we're narrowing in our graph and saying, hey, there's a lot going on right here. Then we pick test points in the intervals to plug into f of x to check the signs. Now, the nice thing is, if we were to look at this function, we actually already knew a clue, the end behavior. Kiddos, what kind of function is this? What kind of power? What kind of degree? Quartic, which means even, which means what would the end behavior be?
Negative.
There's a negative in front, right? So it's going to be now. We don't know the in between, but we know the ends are going to go down like this, right? So just looking, what would we assume? Where would we assume the function is on this interval and on this interval? Below. We would assume that it crosses through and goes down because it can't. Why could it not be up? The only way to go from up to down would be to have another 0, and it doesn't. So we can kind of assume, you know what, I'm pretty sure it's going down, and I'm pretty sure it's going down. But just to double check, because some of these get a little bit funny, we could pick test points in the intervals to plug in. Like intervals. The intervals are the different sections of the number line separated by the 0. So we could plug in something like f of negative 2. We could plug in f of negative 1 half, f of 1 half, and f of 2. Why? I want to figure out exactly how this function is moving and behaving. And some of you probably have a guess based on what you see. We need to know more details about it if we're trying to make a nice, valid sketch. Now, what do we do when we are plugging in? Well, go to the original function and plug in, plug in. But what's going to be easier to plug into? This thing? Or this thing? I think the factored one. Who wants to raise negative 1 half to the 4th power? Not me. So if I were you, I would plug into the factored one. Technically, they both should be the same thing. Plug in the negative 2x squared times x plus plus 1, x minus 1. Why is that my advice? When it's factored, the little facts are easier and shorter. Like, negative 2 times, what's negative 2 squared? PEMDAS would say do the power first. 4 times, what's negative 2 plus 1? Negative 1. What's negative 2 minus 1? Negative 3. And we end up with, what's f of negative 2? 2 times 4 is 8. 8 times 1 is 8. 8 times 3 is 24. And we have a negative, positive, negative. Let's do them in order. Multiply from left to right. Oh man, that's really far down. Yeah. But what do we know from that clue? I have the point negative 2, negative 24. Was I right? Did the graph go below? Yes. And how I could show it on a sign chart real fast is just put a big negative for this entire part, because all the y values are going to be negative. All the y values are going to be below. Now, if I plug in negative 1/2, I end up with negative 2 times negative 1/2 squared times negative 1/2 plus 1 times negative 1/2 minus 1. Ugh. That's okay, do one little piece at a time. What's negative 1/2 squared?
Negative 1/4.
Ah, but a negative times a negative is a
positive.
positive. So I'm going to have negative 2 times 1/4. What's negative 1/2 plus 1? 1/2. What's negative 1/2 minus 1? Minus 2 over 2. I would get a common denominator. That'd be negative 3 over 2. And I'd end up with, oh dear. Does anybody see that this 2 on top would cancel with that 2 on bottom? That's nice. And now I have 4 times 2 is 8. And 3 times 1 times negative 1. Positive 3/8. So a negative 1 times 1, negative 1 times 1, negative 1 times negative 3, positive 3. Now I have the point. Negative 1/2, 3/8. Long story short, what's the sign of this one? Positive. So I'm going to say, hey, it goes above somehow. It goes above somehow. Now I'm going to plug in 1/2. Negative 2 times 1/2 squared times 1/2 plus 1 times 1/2 minus 1. I'm going to end up with negative 2 times 1/4 times 3/2 times negative 1/2. Can change that to a 2 over 2. Can change that to a 2 over 2. I can still cancel out my 2 with one of those denominators. 4 times 2 is 8. Negative 1 times 1, negative 1 times 3, negative 3 times, oh hey, that's 3/8 also. And if you know about quadratics and symmetry, maybe we already could have known that. So what do you think we can say about the last one? It's symmetric, right? They're all copying, true? So then this one's going to be a negative 24 as well. What does the sign chart do? A, it has us finding some extra points. B, it has us thinking about the shape of the graph. So right now, basically from what we've done, I know that the graph doesn't look like this. I know the graph somehow goes up, comes back down, goes back up, and goes back down. Can you guys tell how I know that? Has to come from here, has to go above, has to go touch the 0, has to go above, has to go down again. Now, I don't know exactly how pretty it is until I put all my pieces together, but I do know roughly what it looks like. Okay.
Why did you choose those points? Is it because one of them is totally outside of the 0, the other one is also?
I split my number line up into however many sections in between each of my zeros and the infinities.
But those are not the maximums, right?
Not necessarily.
Okay,
Not necessarily.
they can be those.
but we're guessing that they're probably pretty close. I went halfway in between because usually quadratics are
makes sense.
symmetric. So then if I have a 0 here and a 0 here and a 0 here, this one ended up being this way. I was guessing halfway and I was guessing halfway. Could maybe be a little bit skewed, but we're doing the best we can without knowing calculus. Calculus could know for sure. We can't. Okay. So then, what? Just sketch it? How do we just sketch it? We put it all together. Let me go ahead and get rid of this. We put it all together. What do I mean? What do we have so far? We have zeros. We have points. Anything else? We know the rough shape, right? We know the end behavior, because we already checked that out. It seems to match up with our shape. Okay, well, what can we do? Yeah, we take our graph and we basically say, let's put together everything we know and have a rough picture of what's going on. If we need to, we'll find more points. But hopefully by doing the sign chart, we already have all the points that we need. The zeros we have as -1, 0, 0, 0, and 1, 0. The points we have as -2, -24, -1/2, 3/8, 1/2, 3/8. Just putting together what we have. So let's see how good a graph we can get. We'll go by 1s and a 2s and a 3s. We'll go by 1s and a 2s and a 3s, and we're going to go by 24. We'll make him down there. 24, let's cut him in half, that's 12. Let's cut him in half, that's 6. Let's cut him in half, that's 3. We'll make him a -3, which makes this a +3. This will be -24. So we can go ahead and graph our info and say -1, 0, that's a point. 0, 0, that's a point. 1, 1, oh no, 1, 0, that's a point. -2, -24, that's a point. 2, -24, that's a point. -1/2, 3/8. Oh goodness, that's barely up at all, right? And 1/2, 3/8, that's barely up at all. That's 3. We have roughly. I want you guys to get your graphing calculators out if you have them close. I want you to graph them. See how close it is. Remember, smooth turns. Don't make that sharp, make it smooth. You have to round it. Let's see how we did. How'd we do? Not too shabby, huh? If I had asked you before coming in today, though, graph that thing, you would have been like, calculator, and I would have been like, no. Struggle, right? But what you couldn't do before, maybe at least you have a clue about now. Can anybody, though, look at this and answer the question, what would have made this a whole lot harder? What transformation would have made all my math kind of impossible, at least most of it? What transformation? A translation.
I think horizontal, vertical would mess it up.
If this was shifted down, would I have found any zeros?
No.
Would I have been able to split apart any intervals? And plugged in any key points? If this was shifted down, all I could have found was this right here, right? And I would have had to be like, I don't know. I would have known the ends. I would have known the point if this was shifted down. So see how we would have had to just kind of take shots in the dark and plug in points and hope that we find something good? So is our process foolproof? No. but does it at least give us a start to kind of figuring out some of these functions? Does that make sense?
And the minimum at the 0, 0 is nice.
This one is nice, right?
Yeah.
Because if it had a couple more zeros, right, it would have gone below. But if I had my sign chart, I would have plugged in some of those points, and maybe I would have gotten close and found it. Let's keep going.
1 second. We use 4 points. Like it shows 4 points because it's quartic. But if you had a degree of fit, would you need 5 points?
Well, it kind of depends on the zeros.
Because the ends, then minimums,
Yeah.
then a maximum. We use 5.
Let's do this. Let's say, how could this go wrong? Okay. How could this go wrong? Let's say this is going to answer this question. Let's say we had something like what kind of graph is this? Best guess. X to the third. How can you tell that? It has a swoopy swoop. And even better than that, how many branches does it have? 1, turning point. 2, turning point. 3. So maybe we can count the branches sometimes and kind of figure out roughly what we think it is. Let's go ahead and call this a cubic. It could be like a really stretched quintic, but that's okay. We'll call it a cubic. Question. From what we just did, would we have found a 0? Hopefully. Hopefully. Would we have tested a point on this side of it? Yeah. And would we have tested a point on this side of it? Yeah. But maybe we wouldn't have found any of the other points because we just would have done the sign chart and found 1 here and 1 there. Would that have made us a good graph? No.
No, definitely not.
So maybe we would have needed to find a few more points. Now, could we maybe have found the y-intercept? Yeah. And maybe we would have picked another point somewhere. But the idea is on problem graphs, our zeros and our below and above isn't going to fix everything. So we might have to keep plugging in a few points to try to be like, I hope it's doing something that I can kind of graph. And we might actually end up with something that's a little bit off, right? Or even a little bit more off, right? But we're just trying to do the best guess that we can. Does that make sense? So if you're like, this is not very precise, you're right, it's not. Sometimes it works great, and sometimes it only kind of works. Okay, now here's a different dilemma. What if, let's say we had a quartic. What if we had something like this? Oh, stink. No zeros. We wouldn't have found that. We could have found 1 intercept. Now what?
No, you
I don't know. Just kind of keep going and hope that you get a few, right? Would it have been perfect? No. But we're trying to get a rough idea, right? So sometimes some functions are particularly mean. Now the nice thing is in homework they're not giving you all particularly mean problems. But we just have to keep an eye out that this is an experimentation and exploration, and sometimes we're not going to see the whole picture without going to our graphing calculators for now, for what we know. But couldn't we have known the ends for sure?
Oh, yeah.
Right? And we would have known a point for sure, and we would have guessed that we have to find a few more points, right? And this one, we would have known the ends for sure. We would have known the intercept here, and we could have found the intercept here, and then we could have filled in a few extra points to help us along the way.
And we know the shapes.
And we know the general shapes, but sometimes they're like this, and sometimes they're distorted, right? Just depends. Okay, let's keep going. This multiplicity thing that we kind of introduced. You guys remember when multiplicity? We just said it like 3 slides ago.
Yeah.
How does a multiplicity happen?
If a 0 is repeated.
Yeah. If a 0 is repeated, which happens, here we go, right? When a factor is repeated. We have a multiplicity when a 0 is repeated, which happens when a factor is repeated. And we have 2 different situations. Either we have a multiplicity of an odd number or a multiplicity of an even number. Why are we talking about this? It's actually another clue. It's actually another clue. factors are repeated to a power of k. I actually kind of gave you some of the wording. If k is odd, we're going to cross through. And if k is even, we're going to bounce off. If you're able to factor a polynomial, which remember, these are easier-ish ones than other ones we might see later. If you're able to factor a polynomial, and if a factor is raised to an odd number, actually including 1, 3, 5, 7, if a factor is raised to an odd power, at that 0. At what 0? At the 0 from the factor. Remember, every factor can get a 0. At the 0, you're going to be crossing through the axis, from below to above or above to below. You know that outright. And if the factor is even, you're going to be bouncing off the x-axis at that point. I should say at that, I apologize, at that 0. Because from the factors, we find zeros, right? We're going to go back to the function we were just working with and make sure we understand that some of you guys were like, oh yeah, when we drew it, we bounced off. And why did we bounce off? Well, first of all, from the original factors, and the zeros that they got us, at 0, it had a multiplicity of 2, right? What happened? Even, bounce off. Oh yeah, bounce off. At -1, multiplicity of 1, it's not multiplied, okay, whatever. But as a power of 1, did it cross through? And then at +1, did it cross through as well? It's just another hint, it's just another clue. It's a strategy, a technique, a characteristic that'll always be true. Anyway, not necessarily something to memorize, but something to see. All right, kiddos, I think with this, we're basically done. That's the theorem I already talked about, and then we're homework help. Okay. We might have to leave the intermediate value theorem, but I think we can get this one done. Real quick, before I take a question. This is an example of a later problem from homework. Holy cow, how many things is it telling us to do?
4.
Plenty.
4, and basically, all the clues we've talked about. Leading coefficient test, what are the n's doing? Finding the zeros. Plotting sufficient solution points. Whenever you see this, I want you to think of our sign chart, where we split up the number line or the x-axis with zeros, and we checked or we found points in each of the little pieces of the number line separated by the zeros. Then draw a continuous curve through the points and check with your grapher and see how close you are. Luke, go ahead. Sorry, what was your question?
Just go back.
All right, cool kids. By doing this problem, I'm also modeling to you what I want you to show, which might be different than CalcChat, and it might even be easier than CalcChat. For instance, for letter A, when it says apply the leading coefficient test, Jesse, you're talking about like a graph and how it can be helpful, right? So on this one, kiddos, look at the degree. What degree is it? Cubic. I want you to draw some sort of cubic. You can either draw it like distorted in the sense that it has like Humpty Dumps, like a minimum and a maximum, or you can draw it just normal. I don't care, but this picture is not exactly necessarily what it looks like. What are we looking at first of all?
The ends.
The ends. So draw a picture quick, literally, for letter A when you get there in homework. Circle the ends. Now you have an understanding of how this is oriented. However, I do want you to practice your notation. As x approaches infinity, as x approaches negative infinity. You might hate me now for it, but it does help you later. Ask the calc kids if the little arrows are actually important. They'll say yes. F of x approaches. As we go to the right, where's it going? Positive infinity. As we go to the left, where is it going? All right, A's done. Well, that wasn't bad, right? Letter B says find real zeros, aka what's the first thing you should do? Factor. So take out the x. You get x squared minus 25. Keep going. It's a difference of perfect. I'll just say difference of squares. What do you get from this? We're finding zeros, right? So x is 0, negative 5, positive 5. Sweet. Yes, they're points, but we'll just leave it at that for now. B done. Oh, okay. Technically, all of them have, if you want to help yourself out, a multiplicity of, okay, that's weird. They're all raised to the first power. Letter C. Okay. What do I want you to do for C? Here's what I want you to take a little bit of time. Make a number line. Graph what you have, which is a 0, a negative 5, and a positive 5. Put your zeros. What points do you think I want you to test? You have some leeway. You have some creativity. You just get to choose something. But what's the first place I want you to choose a point from? Negative infinity to negative 5. Choose something there. Sure. Next, I want you to choose something in between here. Do you see what I'm talking about? Choose one from each place. Negative 3 sounds great. If you want to do negative 2 because it's easier to plug in, you can. If you want, you're trying to keep things symmetric, maybe choose in between 0 and 5, 3, or 2. And then beyond 5, if you want to be symmetric, choose 6. And what are we doing? We're making our life better later. We're figuring out when it's below and when it's above and all of that jazz, but we're also trying to find particular points to help. What are we going to do once we have these? Oh, and we're going to see if maybe we can get kind of close to. I think we could. We could. Maybe a little bit off, but we could close. All right, guys, in homework, you might get to something called the intermediate value theorem. Just leave the very end problem or two, and we'll talk about it together on Monday. Sound good? Okay. Oh, here it is. Upside down. Okay. There were a couple. Okay, test corrections on those that were lower. Okay, sound good?
When I run up stuff, I'm like,
Ooh, okay, it's doing something that it's supposed to be doing, just the wrong something. Out here, you have I'll set to little bows. Yeah. You just want to get back to the regular lines.
thank you.
Basically. Because you can tell the vertex, but the other stuff you remove it last time. If yours was 1, you can plug in 1, 0. And I should That's one way. The other way is knowing the grapher and how it normally works. Yours isn't diagonal. So you can go over 1, up 1, over 2, up 4. Looks like a thing, but I'm saying.
Quick question, I didn't want to go over it